Hello, students. Welcome to a new lecture on classical electrodynamics. And today's lecture is lecture number 21. We have been discussing on the Maxwell's equation, and in particular, we have discussed the set of Maxwell's equation in vacuum and in material media. And once again, we have discussed or we have written down the Maxwell equation, which are time independent as well as the time dependent cases. So, therefore, we have a collection of equations, of course, until the last class. And in this direction, we have also seen another important topic, what is known as potential formulation in electrodynamics. So, especially in the last class, we have seen what is meant by a gauge transformation and what is meant by a gauge. So, here the summary or whatever is the conclusion that was done in the last class is written down here. As you can see, that the new magnetic vector potential is given by the old magnetic vector potential plus the gradient of some scalar function. This kind of equation is what is known as gauge transformation equation, or it is known as gauge transformation. That means you are transforming one vector potential to another vector potential. It's a kind of conversion, that's all about it. So you are basically converting from one to the other. It is very similar to what is known as canonical transformation in the case of the classical mechanics. What is the purpose of the gauge transformation is that by performing the gauge transformation, nothing happens to the original magnetic field. So our magnetic field remains invariant under gauge transformation. That is the reason. And then, but then, why do you want to use the gauge transformation? Is to simplify the equation for the potential. That's the reason. If you don't use any gauge transformation and if you don't use any gauge, then the equation, that means the partial differential equation corresponding to the potential, that is the magnetic vector potential, would be a quite complicated equation, and we do not have a solution methodology for that. So that is the reason. So the primary reason for using the gauges and the gauge transformation is to make the differential equation for the potential to be as simple as possible, so that the solution is accessible. So that is the reason. And if you see, the this is the last class summary that I'm showing out here. And then if you're going to fix the magnetic vector potential by the condition saying divergence of A equal to 0, then we can give a name for this gauge, and in particular this gauge is known as Coulomb gauge. If you have a different type of condition, then we can give another name. So we will see what is known as a Lorentz gauge. In the next class, we will see that. But the point to be noted is that you cannot fix directly A prime equal to 0. So ultimately, the point is that you'll have to fix you have to fix the arbitrariness in the magnetic vector potential. That was our objective. But at the same time, you should remember that directly, you can't say, no, removing this del dot, you can't say that the A prime itself equal to 0. That is also actually fixing. Mathematically speaking, fixing is A prime equal to 0 is also one way of fixing. But however, that will not work, because if you directly fix A equal to 0, then the curl of the A is also equal to 0, and curl of A is nothing but magnetic field. And you are saying that magnetic field is also 0. So therefore, fixing the magnetic vector potential directly means without any differential operator, such option is not possible. So therefore, it naturally evolves. That we have seen how it has come. Naturally evolves, in terms of certain differential operator. So that is one thing. And then, of course, this is not important, but ultimately the point is that whatever discussion that we have done in the last class, namely the so-called gauge transformation, is limited to the static magnetic field. So naturally the question is there, what happens if you are going to allow for the time variation of electric and magnetic fields? See, the moment you admit the time variation for the magnetic field, naturally the time variation for electric field naturally takes place. So you can't study the time variation of the electric field alone, not possible. The moment you allow the time variation for one field, the other one is also naturally time varying, and therefore you'll have to study it together. And therefore, you cannot consider only the magnetic vector potential. So once you are going to the dynamic case, that means if you are going to make a transition from the static to the dynamic case, then we cannot consider a single transformation equation like this. So where is that? The screen has gone. Yeah. So this one. So this particular transformation equation, only one equation is there, right? You can't have one equation. We will be having two equations, one for the capital A and another one for phi. Phi is the electric potential. So we need to consider two equations together if you are going to make a transition to dynamic case. So that we will do in the next class. But what is the purpose? Then what is the plan for the today's lecture? Is that we would like to understand the Maxwell equation more in detail. We would like to interpret what is the meaning of the equation. Of course, we have done, of course, mathematics in terms of vector calculus, applying some theorems and rules, etc. Ultimately, we have established, four equations, and what we call them by the name Maxwell equation. But the point is that once we have written down that, we would like to understand and interpret the meaning given by each one of these equation, and we are also interested to know how the equation itself is working in nature, how it's working. And the most fundamental question that one asks is that whether all the four equations are really independent of each other. Okay, what is the meaning of that question is, can we derive any one Maxwell equation from the remaining three? If you are able to successfully derive any one Maxwell equation from the remaining three Maxwell equation, then we say that all the four of them are not independent. So we are asking the question whether such a thing is possible or not. And we are going to make a conclusion that the answer is no. That means all the four of them are independent of each other. Okay, which means that none of them can be derived from the remaining. So these are the things that we are going to see in the today's class, and this requires a little bit of analyzing and understanding the Maxwell equation. And for that purpose, I would like to first of all give a 1 minute introduction to what is meant by a homogeneous differential equation and inhomogeneous differential equation. You already know how the classification is there, but I would like to mention a point so that it is quite comfortable when you are looking at the Maxwell equation. You must be in a position to identify which of the Maxwell equations are homogeneous and which among them are inhomogeneous. So let me therefore go to the board, and I will start explaining with a particular example. So here I would like to show how we can classify the partial differential equation into homogeneous or inhomogeneous. So for that, you consider a very simple equation which is written down here, and we are going to use the uh, suffix notation like this. That means ux will be the partial derivative of u with respect to x, and so on, so that you don't have to write the expression looking like this. Instead of this, you can write down uxx. This can be written down as utt, etc. Okay, so the question is this: what is the question now? Question is, you have to tell whether this particular equation is homogeneous differential equation or inhomogeneous. So how to classify? So the methodology is quite simple. What all you have to do is, you have to write down all the dependent variables on the left hand side, and once you write all the dependent variables, all the terms containing dependent variables on the left hand side, find out what is left out. If anything is left out, then write it on the right hand side. Otherwise, your right hand side will be 0. So this is the idea. Once you finish this, then based on the right hand side, you can make the decision. So I would like to therefore write down first of all uh, whatever I am explaining. So collect all the terms containing the dependent variable and then put it on the left hand side. And whatever remains, you put it on the right hand side. That's all. And if the right hand side is equal to 0, then the differential equation is homogeneous. Okay. Otherwise, it is inhomogeneous. So the concept and other things are quite simple. But now we need this information, so better you have to refresh your memory. So here, how do you understand is that the dependent variable, that means unknown quantity, u is the unknown quantity, and it is also known as dependent variable. The x and t is the independent variables. So we don't have to worry about independent variables in the present discussion. So this particular term is also a dependent variable term, and this term is also dependent variable term. Therefore, all of them should be written down only in the left hand side. So if you put it on the left hand side, then what will be there on the right hand side will be only 0 will be there, isn't it? That is the idea. So you have to put a minus of this equal to 0. And since you have a 0 here in this particular case, now we can make a conclusion that this particular equation is homogeneous differential equation. So that is the idea. So therefore I will also write down, or I will give you another example so that you can verify whether it is homogeneous or not. So now the first equation, what is the answer? Homogeneous. And similarly for the second equation, what is the conclusion? So second equation, you can immediately conclude there is a ux here, therefore dependent variable is there. Uxy, dependent variable is there. Dependent variable means what? Unknown quantity. U is the unknown quantity. X and y are the independent variables. And therefore this is also dependent. Therefore it should be on the left hand side. 3 times u. So this u is also dependent variable. It should be on the left hand side. So therefore take it to the left hand side. And what is remaining? So once you decide all the terms, nothing else is remaining. Therefore right hand side is 0. And therefore once again this equation is also homogeneous. So similarly, if you are going to consider another equation, let me write down another equation, something like u times x into second derivative of u plus, let me finish writing this. Yeah, so that is the equation that we are going to have. So here also the conclusion is quite simple. You have u here, whether it is u, when one u is there or derivative is there, that doesn't matter. If any term, whether it is derivative or without derivative, if the unknown quantity is present there, then that should be on the left hand side. So x, y you have to forget. U is there, so it should be on the left hand side. Here also u is there, it should be on the left hand side. And here also the unknown quantity is there. This should be in the left hand side only. Therefore, you can push it into the left hand side, and therefore nothing is remaining on the right hand side. And therefore, the conclusion is that this equation is also homogeneous equation. If you're asking about the linearity and the non-linearity, then that is another story. So here you'll have to consider the power of the unknown quantity. So unknown power is 3. Here you see unknown power is 2. Here unknown power is 1, and here unknown power is 1. So whenever, of course, there is one more power is there is, this is unknown power 1, and there is another unknown power 1. Therefore, the total power is 2. We can consider 2 here. Okay, even though derivatives are there, you don't have to worry about that. We are going to make a conclusion that there is one unknown power 1, another unknown power 1. So total power is 2. So the point to be noted is the moment you say that the unknown power is greater than 1, greater than 1 is important. Okay, the moment you say that the unknown power is greater than 1 or less than 1, in any case exactly 1 is the only condition for linearity. Okay, so the moment you say that the powers are like greater than 1 or less than 1, then we will make a conclusion that this is a nonlinear differential equation. And come to this u to the power 1, here also power 1, here also power 1. So exactly 1 is there. Exact 1 means linear. Anything less than 1, anything greater than 1, then we say that it is non-linear. So therefore this is a linear differential equation. Once again, the power of u here is 1, here the power of u is 1. Therefore this is also linear differential equation. So that is the, so let me write down here the homogeneous is our conclusion now. And similarly, at least I will give you another example so that you will be able to understand when the inhomogeneous situation comes into picture. So equal to x square plus y square plus dou square u by dou y square. So this is an example where you can see what will happen. You have unknown left hand side, unknown left hand side. This is not unknown. See the x square, this term x square does not contain any unknown. Therefore, this must be in the right hand side only. There is a y square. Y square also doesn't contain any unknown. Unknown is u. Therefore, this cannot go to the left hand side. This is dou square u by dou y square. This has to go to the left hand side. So you have to put it to the left side, and two terms are remaining here, which means that the right hand side is not equal to 0, and therefore we make a conclusion that this is a inhomogeneous differential equation. In addition to this particular thing, and this is also a nonlinear differential equation because unknown to the power 2 is there. So u is there to the power 2. Forget about derivative, no need to worry about the derivative is there, no derivative, nothing to worry. So there is an unknown quantity and then power is there. Therefore it is nonlinear. But there is a x square here, right? Those things you don't have to worry. You have to worry only about the unknown variable. Okay. Other than unknown variable, whatever is there, you don't have to worry about their powers. And similarly, here also same thing. Here you see unknown power 1 is there, so it is linear. There is x square is there, y square is there. This one you no need to first of all worry. This is not at all unknown variable. Okay, only ux is the unknown variable. Therefore, whatever power is there for the independent variables, simply there is no need to worry. Ultimately, this equation is a linear differential equation. Okay, so the last equation is a non-linear differential equation, and it is also inhomogeneous. So of course, this is of course quite familiar to you, but now we are interested to keep this in memory, so that when we are looking at the Maxwell's equation, you have to classify the Maxwell equation into whether it is linear equation or non-linear. At the same time, you should also be able to classify which of the four Maxwell's equations are homogeneous and which of the remaining are inhomogeneous. So that is the reason why we are doing. Okay, let us now go back to the original discussion, namely on the Maxwell equation. I'll go to a different place in the board, and then I will show the set of four Maxwell equation. Yeah, here it is. Okay, so today's discussion is on learning the details about the Maxwell equation, where both of them are time dependent. So now no more statics. Okay, all the discussion corresponding to the static cases is already completed in the previous lectures, and we are going to discuss only the time dependent cases in all the lectures uh, that we are going to see in future. Okay, so there are several points are there to be discussed, even though it looks only four of them. So there are several points are there. Therefore, let us see one by one. All the four differential equations are partial differential equations. None of them are ordinary. Okay, that is the point that you can understand. And the second point is that there are space derivatives are there, dou by dou x, dou by dou y, dou by dou z, and you also have time derivative. So you can have, that means everywhere you can see there is a first order space derivative, first order space derivative. Everywhere you have the first order space derivative. In addition to that, you also have the first order time derivative is there. So whenever time derivative is present, we that particular equation is known as the temporal evolution equation. Evolution means what? How a particular physical variable evolves with respect to time. That is the meaning. The dou b by dou t is equal to this much means, what is the meaning of this is, this particular equation tells you how the magnetic field vector evolves with respect to time. If time changes, how b will change. How b will change mean, that means as time changes means, that's what we say, as time progresses. This is what we say temporal evolution. And this is very important and very characteristic feature of any dynamical system. So from the classical mechanics course also, especially when you are learning the Hamilton's equation of motion, we have seen that the Hamilton equations are actually differential equations that are first order in time. This is very important. Whenever you have a differential equation that is first order in time, it is representing a dynamical system. So it's very important characteristic, namely that the temporal evolution of any dynamical system will be first order in time, which you already learned from the Hamiltonian mechanics. Okay, if you are going to write down in the form of the Newton's second law, or if you are going to write down the equation in terms of the Euler-Lagrange equation, you don't see this. Okay, because you don't see the first order time derivative. But when you reconstruct your mechanics in terms of the Hamiltonian formulation, okay, which means that the Hamilton's equation of motion, they represent or they show this kind of a behavior, namely the time evolution equations are first order. And this is quite very important. And even in the case of the fluid dynamics, for example, your Navier-Stokes equations are first order in time. So therefore, wherever there is a dynamical system, okay, the physics of the dynamical system will be governed by a differential equation that is first order in time. So this is quite a very important concept that lies across the physics. Okay, it's not very particular to any particular area like electricity, magnetism. It is there throughout the physics. So this is very important. And there are more important point is that all of them are linear differential equation as long as you are going to consider linear homogeneous isotropic material. So there is an underlying assumption that throughout this particular course that you are going to study in the MSc, we will be considering only the linear homogeneous isotropic material, whether it is dielectric material or whether it is magnetic material. So that assumption guarantees that all the four differential equations are linear. You don't have electric field to the power, nothing electric field to the power 1 everywhere in any equation. Similarly, magnetic field to the power 1, if it is less than 1 or greater than 1, automatically it becomes non-linear. And therefore, as long as you are going to study the only the linear dielectric material and the linear magnetic material or vacuum, under that limitation, the Maxwell's equations are linear differential equations. So these are the points, and of course, as I already told you, that electric field is a function of x comma y comma z because space derivatives are there, and in addition, it is a function of time. So x comma y comma z comma t, four variables. So it is a function of four variables. So these things has to be at least written down at least once. And in addition, I would like to now see which of the equations are homogeneous and which among them are inhomogeneous. So that means first of all you'll have to identify which variables are unknown quantities or dependent variable. Both are same. Unknown or dependent variable. Both are identically same. So what is unknown in the first equation? Electric field. And therefore keep all the terms containing electric field to the left side. Whatever is not electric field, that should be on the right hand side. So in that way you have to write down. So let me therefore write down. So in this equation there is nothing to do, it is already there in that particular style. Therefore all terms containing electric field to the left side, and all terms not containing electric field to the right side. You have to write down like that. And so once you write down, your right hand side is not equal to 0, and therefore this equation is inhomogeneous differential equation. So that is the point. And coming to the second equation, what are the unknown quantities in this expression is the electric field is unknown quantity and magnetic field is also unknown quantity, because they are the quantity to be determined, right? Essentially, what is the entire story of the electromagnetism is that we have charge densities and we have current density. They are the sources. These sources are going to produce the field. So our job is to find the field. Our job is to find the field means field is unknown to you. Therefore, electric field is unknown to me, magnetic field is unknown to me. All the unknown quantities should come to the left side. Therefore, this cannot stay on the right hand side. So take it to the left side and then rewrite this equation. Once you rewrite like this, what is there on the right hand side is 0 is there. And that is clear, right? And therefore, now you can make a conclusion that because 0 is there on the right hand side, this particular equation is homogeneous differential equation. And coming to the third equation, anyway, unknown quantity is the magnetic field. It should be on the left hand side. It is already there. And therefore, nothing is there on the right hand side. So there is nothing to do here. And of course, clearly, the divergence of B equal to 0 is homogeneous differential equation. And coming to the last equation, here what are the unknown means? Magnetic field is unknown, electric field is unknown. What about current density? Current density is a known quantity. Similarly, charge density is a known quantity. So we are going to have charges and we are going to provide current. And because of the presence of the charges and the current, you are asking the question how much magnetic field and how much electric field is arising. And therefore, current density is a known quantity, which means that this will not go to the left hand side. That is the meaning. So the magnetic field term will be on the left hand side. Electric field term also you have to take it to the left hand side because these are all unknown quantities. and what is left out is mu naught into j will be left out, that will stay on the right side. So you have to rewrite like that. So whatever is left out is the source term, and as you can see that since the mu naught times j is there, which is not equal to 0, we say that this is inhomogeneous differential equation. Okay, you can say inhomogeneous or you can say non-homogeneous, it's all fine. Okay, and once this is clear, whatever I explained, I will just write down. And coming to the, I would like to give some number. Let us give the equation number for the homogeneous cases first of all. So which are homogeneous? 0 0 is there, right? 0 0, they are the homogeneous equation. Now in these two equation, which is very very simple equation out of these two, 0, this equation is the very simple equation, del dot b equal to 0. Therefore I will give the equation number 1 for this. And then once if I say that this is equation number 1, then the second or the next homogeneous equation is this one, and this is a little bit complicated than that, and therefore I will call this by the equation number 2. Now once this is over, the remaining two, that means this particular equation is inhomogeneous, last equation is also inhomogeneous, and out of these two the simple equation is divergence of E. Therefore I will call by the equation number 3 for this, and a little bit complicated equation finally we will call equation number 4. So this is the reason why we are giving the equation number, and ultimately remember that all the quantities are functions of space and time. This is very important. Even though I have been telling this several times, better I write down at least once. We have not at all written any time earlier, so better at least we will write down. What I am trying to say is that all the field, electric field, etc., are functions of space and time. So what is IH? IH is inhomogeneous. That's all. H means homogeneous. Okay. So H means homogeneous equation. IH means inhomogeneous equation. Fine. And then simply you write down that electric field. Okay. If I say electric field, then electric field is a function of R and T. That is what I am trying to say. You have to write like this. Everywhere you have to write like this. But the moment you understand that everything is a function of R comma T, we don't have to write in all the places. So that is what at least I would like to write down once. The point I am trying to say is that every E should be written like this. Every capital B will be written down like this in this equation. So then the equation looks a little ugly. Okay, it looks a little lengthy and ugly. So that is why I did not write. But at least you should remember that every electric field or every place where rho comes, every place where capital J comes, they are all functions of space and time. That is the meaning that you should remember always, because this is going to discuss the complete dynamics. So that is the point that is very important. And once this is clear, now we will ask the question, how many how many variables are there to be determined? Even though we say that electric field is to be determined, but electric field is a vector quantity, right? So I want to write that. So vector quantity means if you are asking a scalar number, then it will be 3. 3 scalars will make one vector, right? So I want to write that explicitly so that you can make the total. Let me first write down and then show. Yeah. What I am showing is the same Maxwell equation is written down here for convenience, and I have rearranged them. In what way I have rearranged is, first of all I have the homogeneous equation, and after that I have the inhomogeneous equation. So the inhomogeneous equation I am showing in a different color. That's all about it. And I am maintaining the equation number 1 2 3 4. It is the same equation that we have written. Okay. So the same. This is equation number. Okay, not serial number. So once you understand this, we are asking the question: how many unknowns are there in this equation? Of course, it is quite trivial. B vector is unknown, but remember, B vector means x component is there, y component is there, z component is there. Therefore, actually, it is three variable, not a single variable. Therefore, that has to be written down. Okay, if you don't write, it appears that okay, B only. Okay, 1, you will think that it is 1. It is not 1, it is 3. So I will write that now. So you have the x component, y component, and the z component. So there are three quantities are there which are unknown quantities in this equation. That is first point. Then we ask the next question: how many equations are there corresponding to this? So you count how many equations are there. Divergence of b equal to 0. How many equation? So in order to count, you should know whether it is scalar equation or vector equation. When you take the divergence, it is automatically scalar. Therefore, scalar means only one. Therefore, this is a single scalar equation. So I will write down that this is a single scalar equation. Okay, and finally, you already know whether the equation is homogeneous or not. I will simply write down H. I think that is enough. H means homogeneous. Okay, now this is known, and now you can fill the remaining box. It's quite simple. Now you tell what are the unknowns here. Electric field is unknown. That means Ex, comma Ey, comma Ez. Similarly, capital B is unknown. Bx, comma By, comma Bz. Therefore, 6 unknown quantities are there. That's what you have to write down. Then how many equations are there? Now this particular equation, it looks like one equation, right? But it is not one equation. That's what I want to say. This is a vector equation now. There is no divergence. This is a curl, right? Therefore, this is a vector equation. So one vector equation is equivalent to three scalar equations. One scalar corresponds to one direction: x direction, y direction, z direction. And therefore, the right hand side is a zero vector. This is a zero scalar. Okay, zero vector means what? 0 into ax vector, that is unit vector in x direction, plus 0 into whatever you call j cap, and then 0 into k cap, ijk. That's what I'm talking about. And therefore, this equation is actually three scalar equations. Therefore, I'll write down that. And similarly, this is clear. Once this is clear, homogeneous, you fill out, and then the remaining things I will continue to write so you can understand what is happening. So you have the three unknown quantities, and this is actually a one single scalar equation. And then once again, this is only a yeah, this is a inhomogeneous equation. Yeah, so IH. Here, of course, capital J should not be included. Capital J is current density, that is a known quantity. And three scalar equations are there. And once again, this is an inhomogeneous differential equation. So that's all fine. But then now the question comes, why did we do this? Okay, why we are worrying about all this thing is because we would like to know totally how many unknowns are there in this Maxwell equation. Because Maxwell equation, it looks like four Maxwell equation, right? But you count now how many equations are there. So there is a 1 here. You count it. 1, 1 plus 3. 1 plus 3 is 4. 4 plus 1, 5. And then 5 plus 3, 8. So actually there are 8 scalar equations are there. Maxwell equation means 4, right? When you say Maxwell equation 4, but it is not 4 now. You have 8 equations in terms of scalar. Because ultimately all simplifications are being done using scalar only. So therefore, so there is a 8. And similarly, you'll have to count how many variables are there. You can't count just like that because same bx by is also repeating here. Okay, this bx and this bx are identically same. So you can't count like that. So there is a 3 here, then 3 plus 3 6. 6, and this is also repeating, so no need to count. This is also repeating, this is also repeating, no need to count. So totally how many variables are there means only 6 variables are there. So therefore let us write down the total now so that we can do some bookkeeping work or accounting. So total number of unknown quantities to be determined is 6. But at the same time, how many equations are there? 8 equations we have. Count it. Okay, 8 equations. Okay, that's all about it. Now the question, now why did we do this kind of counting is your basic algebra or whatever linear algebra that you study, it clearly tells you that number of unknowns and the number of equations should be equal. Only when you have number of unknowns and the number of equations are equal, then only you can find out a unique solution to the problem. If any one of them is less, then either the problem is under determined problem, or it could be a over determined problem or over specified problem. You can't have more number of equations than the unknown, etc. So this you already know from a simple algebra or what you call the linear algebra. So now therefore the same question now comes here. The question is that we are having more number of equations, isn't it? So once I write down the statement will be clear. Let me therefore write down here. Our conclusion from this kind of analysis, what is the conclusion is that the number of equations that we have is not equal to the number of unknowns. If it is the case, the natural question is, do we have a unique solution? Or first of all, whether solution is possible or not. So do we have a unique solution to the problem? So that is the question. So initially, at first sight, what happens is it appears as if there is some kind of a paradox, or it appears as if some kind of contradiction is there. It appears like that. But however, there is no contradiction. Answer is provided by the Helmholtz theorem. And what is Helmholtz theorem? We have already seen in the last class or the previous to last class. So the statement is we have seen it, and once you understand the Helmholtz theorem, you get the clear answer. And our clear answer is that there is no trouble in this particular situation. We have unique solution, no doubt about that. And the number of equation is not equal to number of unknown. That will be resolved. How it is going to be resolved? Probably I will explain. Now, why it appears to be a paradox or why it appears to be a contradiction is that these equations are appearing in terms of divergence and curl. Okay, when you are learning linear algebra, at that time we say that number of unknowns and number of equations should be same. At that time it is quite simple because equations are algebraic equation. Now we don't have any algebraic equation. We have differential equation. These are the differential equation. Not only the differential equation, this is much more specialized differential equation in the sense that the derivatives are actually coming in terms of divergence and curl. This is not just like randomly you write something like dou square u by dou x square. It's not like that. It's not randomly coming. It is some kind of specialized derivatives are there. So those special derivatives are actually divergence and curl only. So there is something special about the gradient operator, divergence operator, and curl operator. Each one of them have geometrical meaning in the three-dimensional Euclidean space. So ultimately, there is some geometry going on behind the scene, which is not visible to you directly. And the Helmholtz theorem actually tells that. So Helmholtz theorem is also known as Helmholtz decomposition theorem. So what all Helmholtz theorem says is that the particular vector can be uniquely determined. Okay, the particular vector, it could be any vector v, can be uniquely determined if the divergence and curl are known quantities to you. That's all about it. That is Helmholtz theorem. It is also called a decomposition theorem because one of the two quantities, namely one of them, because two of them are there, right? One is divergence and another is curl. One of them is known as the longitudinal component of the vector v, and another one is known as the transverse component of the vector. That means the unknown vector v can be decomposed into transverse component and longitudinal component, and both of them are perpendicular to each other. So once you determine two components perpendicular to each other, we say that the vector itself is uniquely determined. That's all about it. So let us not go into the detail of the Helmholtz theorem because you'll have to realize how the geometry works there. Okay, where you understand what is gradient, right? The gradient represent the direction of maximum change. That is called a directional derivative. Similarly, divergence will talk about whether the vector valued function is diverging away from a point, and the curl of the vector will tell you whether a particular vector is circulating around the point. So this is about circulating around the point. This is deviating away from the point. Gradient will tell you the direction of maximum increase, and finally the Laplacian operator will tell you the arithmetic mean of all the surrounding points about a point. So these are the geometrical interpretation of the divergence, gradient, and curl and Laplacian. All these things are there involved in obtaining the Helmholtz theorem, and ultimately, okay, you don't have to worry all of them, but for the time being, this is enough. What all is enough is that provided that you have the divergence and curl, these quantities uniquely determined, that you can easily see. So I will at least I will write down that this is clearly visible from the Maxwell equation. I will just show that by writing whether divergence and curl is specified or not in the Maxwell equation. So here I will write down. So equation number 3 is okay. Anyway, I don't want to go back and forth. You are writing, right? So you know what is equation 1, 2, 3, 4 now. So equation 3 is the divergence of the vector field. And then similarly, the corresponding curl you have to search. So where is the corresponding curl is equation 2. So that means your Maxwell equation 2 and Maxwell equation 3, they give you or they specify the divergence of electric field and curl of electric field. That is what is this. So when the divergence and the curl is available to you, then that vector quantity is determined. So here, what is that vector quantity? Capital E. So hence, and therefore hence we can say that electric field is uniquely determined. So one problem is solved. And similarly, find out the equation number for the remaining two. So equation number 1 tells you the divergence of B, and equation number 4 will tell you the curl of the B. And since divergence and curl is available, once again capital B vector, namely magnetic field, is uniquely determined. So one thing is clear that whether you have the unique solution or not, that is a question that we were having. At least this problem is now solved. That means there is no doubt about having any problem in the unique solution. Unique solution is available, so there is no contradiction. That is one thing. But however, there is one small confusion or one small doubt is still there. What is that is, we have seen that there are 8 equations but 6 unknowns. Where is the explanation for that? That explanation is not visible here. Of course, it is there, but it is hidden. It is hidden inside the Helmholtz theorem. So, if you want to understand why there is 6 there and 8 here, some extra equation is there, like that, the doubt comes. And in order to understand that, we can have an alternate explanation. Okay, we don't have to worry about the Helmholtz theorem. Without the Helmholtz theorem, we can understand in a different style. So I would like to explain that now. Okay, so for the time being, we have the, do we have the solution means yes, that's all about it. And let me go to another place in the board and I will explain in a different way. So here what is the plan is that we would like to understand the Maxwell equation in much better way, without using the Helmholtz theorem, so that you will be in a position to account for why the 8 equations are there. What is that extra equation doing? We would like to know what is the job of the extra 2 equations. So that is what we are going to do. So purpose I already explained, and let us do a simple mathematics. Of course, quite simple expression we have to do. Let us first consider the curl equations. I will first tell what we are going to do. Maxwell equation contains 2 divergence equation and 2 curl equation. You forget about the divergence equation. You consider only curl equation now. So one of the curl equation is this one. This is the simplest curl equation that you have. And now you take the divergence on both sides of the equation. Take the divergence on both sides of the equation. And then, yeah, from the mathematics, you know that divergence of curl is always 0. Always 0. So left hand side is 0. 0 by mathematics. Okay. On the right hand side, of course, time derivative and the space derivative are exchanged. and that's all over. We got one conclusion. The conclusion is that the time derivative of the divergence of the magnetic field is zero. And this is very important. So I would like to highlight, or I'll put a box. So this is the conclusion. The point that I would like to say is that we started with the curl of the electric field, which is the original Maxwell equation, and then did some mathematics here, and we got a conclusion. Okay. Remember, this is not Maxwell equation. The last equation, this is not at all Maxwell equation. But you have one Maxwell equation. Remember, divergence of B equal to 0. That is not this. This is different. Okay. So don't confuse divergence of B equal to 0 as a Maxwell equation and not that. So don't try to confuse those two things. And we are going to understand this equation. So let me therefore further write. We would like to understand this in a better way. So let me explain further. So what you do is you try to rewrite the starting equation. How we are going to rewrite is, let me write the time derivative first, and then whatever is I'm simply rearranging. That's all about it. Okay, that's all. So by rearranging this, we are trying to understand the equation. And what is the conclusion because of that? This is the conclusion. I'll write down that. This is the conclusion. Okay. So that is the time derivative of the divergence of B equal to 0. That is the conclusion till now. So both of them are important equation, and maybe I'll put some highlight. I'll explain this, how to understand this particular equation. So let me put a box. Okay, fine. Now, first thing is that why did you rearrange? Rearrange means what? Time derivative I am writing in the left hand side, and this one, whatever is there, you put it on the right hand side. Now, why you want to write like this is that this is how the equation will look in the case of the classical mechanics, in particular Hamilton's equation of motion. You should remember how it looks like. The Hamilton equation of motion will is like q dot and p dot, right? So the dot is the time derivative. So here I'm trying to uh, give some similar kind of appearance. Here you have the time derivative, so it is actually looking like b dot. Okay, magnetic field dot. Dot means time derivative you have. So this kind of time derivative is actually the meaning is that it is going to tell you the time evolution with respect to time, how the magnetic field will evolve. That is the meaning if you write it on the left hand side. So that is why we are rearranging like this. So if you write like this, what is the meaning is that this particular equation will dictate how the magnetic field will evolve with time. That is okay. That's clear. But then what is the purpose of doing some additional mathematics here? Some 2 3 steps we have done, right? So what is the purpose? The purpose is that we got a conclusion here. This conclusion is very important. Only thing is that we have to understand what is the meaning. The meaning is very clear here. There's a time derivative is there, and then divergence of B is there. The meaning is that this particular equation is satisfied at all time. That is the meaning of this, because dou by dou t is there. So if you integrate this equation on both sides, I'll be getting a divergence of B equal to constant. Isn't it? Because dou by dou t is there, right? So if I integrate both sides with respect to time, then I'll be getting divergence of B equal to constant. But if you do that, then we will be missing some information. That is why we did not integrate on both sides. This equation will tell you that all time is there. That is very important. Okay. So what is that you are understanding from the last equation is that the evolution of the magnetic field is not having complete freedom. Magnetic field does not have complete freedom to evolve on its own, but instead magnetic field is constrained. That means magnetic field is restricted to evolve under this condition. This is very important condition. uh, of course, in the classical mechanics, you already know when the dynamics is taking place, there are restrictions, there are constraints. In classical mechanics, you have two options. Okay, you can have a dynamical system without constraint, possible. You also can have dynamical system with constraint. Both options are possible. But in electrodynamics, it is not so. Magnetic field cannot evolve without constraint, not possible. If magnetic field has to evolve with respect to time, then it has to evolve under the restriction, namely that the time derivative of the del dot b is 0. This time derivative actually means that all the time. That is the meaning. For every time, this should be true. Okay, that's the meaning. This is quite very crucial. Okay, the nature works like that. So actually, this mathematics clearly tells you how the nature is working. So magnetic field does not have 100% independence. It cannot evolve on its own. Whatever value cannot be taken by the magnetic field. Magnetic field cannot take any value as it likes. Not possible. That's the meaning of this equation. So therefore, I will try to write some explanation whatever I told you now, and maybe I also told you about the Hamilton equation, right? So probably I will write the Hamilton equation so that it will be easy for you to visualize. So the Hamilton equation is, this is the equation. So if you compare this, it will be quite clear for you, or whatever is there. So q dot is given by the partial derivative of the Hamiltonian. P dot is given by the negative partial derivative of the Hamiltonian. Now the q dot is nothing but dq by dt. P dot is dp by dt. So this equation tells you how the q will evolve with respect to time, how p will evolve with respect to time. That means how the position will change with time, how the momentum will change with time. That is known as the evolution equation. So these two equations are known as the evolution equations. And similarly, this equation is the evolution equation for the magnetic field. And for this, the restriction automatically comes. And here in classical mechanics, you don't have restriction, it is optional. You have to decide in your experiment, you may have restriction, you may not have restriction. But in electrodynamics, it is not so. This restriction always comes together. You cannot eliminate. There is no way you eliminate this restriction. So that is a point to be noted. So okay, so one important conclusion we have made. So therefore, I would like to write down all the explanation. So in the dotted notation, you can also write like this so that it looks like Hamilton equation. But only thing is that the dot represents partial time derivative. Okay, now if you integrate this, what happens? I already told you, but let me write down. If you integrate this, then I will be getting the divergence of B equal to a constant. Could be a constant, right? Instead of 0, it's constant. But however, there's a point to be written. Now only you'll have to see the Maxwell equation. But Maxwell equation has something called divergence of B equal to 0, right? And what is that? So that is the place where you have to make a conclusion that experiment proves or experiment provides that this particular constant is 0. So this is something that you'll have to be careful. This is not the Maxwell equation, okay? But divergence of B equal to constant is not Maxwell equation. E equal to 0 is only Maxwell equation. Okay, so I think that explanation is enough, and probably I will write down the conclusion. Okay, I would like to write down the conclusion. The conclusion is that the curl equation determines the magnetic field. This is very important. The curl equation determines the magnetic field, whereas whereas the divergence equation serves the purpose of constraint. Okay, if you are able to understand this one line, it's all fine. Okay, so the purpose of all this calculation is to demonstrate this kind of conclusion. So curl equation is going to determine the field, divergence equation will serve the purpose of constraint. So that will be our first conclusion. We can also make a second conclusion now based on the second curl equation. We also have another curl equation, right? Only thing is we have to do a similar kind of mathematics, and it all takes only 2-3 steps. Okay, let us repeat the similar steps now. I will first of all write down what is the curl equation. Del cross B equal to mu naught into J plus mu naught epsilon naught into dou E by dou T. Okay, as usual, Take the divergence on both sides. Whatever we did, no, same thing you have to do. Take the divergence on both sides. So divergence of the curl of the B equal to you simply write down divergence of divergence of entire thing. Oh, I'll erase this. I have to write down divergence of the entire thing. Simply copy whatever is there, and that's it. And okay, by mathematics it goes to 0 on the left hand side, and on the right hand side what happens, mu naught is common, so let me remove it. Mu naught is common. What is left out is divergence of J, plus you have epsilon naught, then time derivative, let me write first of all, and then a divergence of electric field. Okay, that's all about it. And because divergence of J is coming here, current density, we will use the continuity equation. So we will bring the continuity equation. No, otherwise you don't know, right? What is divergence of J? Divergence of J means always bring the continuity equation. So from that you can tell that it is negative of the dou rho by dou t. So 0 equal to negative of the dou rho by dou t plus the time derivative of, I am trying to take it inside and write a displacement vector d. So this is clear, right? Epsilon naught into E. What is epsilon naught into E? D. Of course, you can assume that epsilon r is also there, which is equal to 1. There is a 1 here. 1 into epsilon naught. That 1 is actually epsilon r, relative um, electric permittivity. So epsilon 0 into epsilon r into E, that combination is actually D vector. So the advantage is that, this kind of symbols will disappear. That's the reason. And now that you have both side, you have time derivative. So I can take the time derivative common. I'll take time derivative common and write down. Minus of rho, that's all about it, and that's equal to 0. And this is once again, this is the conclusion and very important. So keep this in mind, and we will now make a conclusion. How to make a conclusion is that your starting equation, let us rewrite in a different style. It's only rewriting, okay? So let us remove this mu naught and epsilon naught. That is the reason. Let us divide the equation by mu naught, and then bring the current density to the left hand side, and then epsilon naught into E, as usual, make it a displacement vector. That's all. So we are doing a simple rearranging. And then once again, remember what is this B by mu? B by mu is how much? H vector. So you are going to assume the what you call the constitutive relations for the linear dielectrics and the linear magnetic material. So epsilon naught into E, that will be equal to the displacement vector, and B by mu can be written down as the H vector. And that's all about it. And that is fine. And then we will write down the time derivative first. So I would like to write down the time derivative first. So I will say that it is a d then dot then vector. You know why we are putting dot? Looking like Hamilton equation. That's all. So curl of the H vector, and then what is left out is minus of the J vector. So ultimately what happens is the same Maxwell equation. Remember, the same Maxwell equation has been rewritten in a different style. And what is the advantage of this particular style is that left hand side clearly tells you that it is going to talk about the time evolution of the displacement vector. So this particular equation, whatever equation that you have written here, is nothing but it is same as this, and we can now understand in a better way. In what way? Your understanding is that this particular equation tells you how the electric displacement vector will evolve with respect to time. That's all about it. But remember once again that the electric displacement vector cannot assume any value as it likes. That is a very important conclusion. How do you know that? Means that is what is the highlighted expression here. You got it right. So I will write down the same thing. I will say that this particular d dot represent the time evolution of the d vector, and The time evolution cannot happen completely independently, but instead it is subject to the condition. What condition means? Just now you derived, right? Here it is there. So this one. So you can simply copy. That is the condition. So dou by dou t of divergence of d minus rho equal to 0. That is a condition. And once again, remember that the dou by dou t means all the time, all the time, all the time. So that is the meaning. So all the time this condition should be satisfied. So the meaning is that divergence of the displacement vector minus of the rho, that quantity should be a constant for all the time. And then you have the so-called Gauss law, right? That is an experiment. So the experiment provides, or experiment gives the proof that the constant is 0. Now, this statement is little bit, you have to be more careful to understand, otherwise this statement is little, it will be little bit confusing. This is clear. There is no doubt about this equation. You got it, you derived it here. Now the last line is very important. How do you understand this is, you should remember that there is a Maxwell equation saying that divergence of d is equal to rho. There is one equation. So you compare with that equation with this equation. Now integrating on both sides, what happens? You get a constant. But what is the Maxwell equation says? Maxwell equation says that divergence of d should be equal to rho. If it is equal to rho, then what should be the constant? It has to be 0. Only if this is 0, I can say that divergence of d equal to rho. And who is going to fix the constant 0? How do you know? Experimental evidence it is. It is not mathematics. Divergence of the displacement vector equal to rho is basically what? It is Coulomb's law. Coulomb's law only has been rewritten in this differential form, and therefore the constant is fixed by who has fixed the constant means nature is fixing. Coulomb is not fixing. Okay, nature is fixing the constant to be equal to 0. That was discovered by Coulomb. So this is very important, and therefore the meaning, ultimately what is the meaning of this equation is, the ultimate meaning is that the divergence of d minus rho equal to 0 should be maintained at all time. That is the meaning. It should be maintained at all the time. This is what is known as the restriction. Restriction means what do you call, the kind of imposition you are imposing. Okay, you have to always satisfy this condition only in such a way, okay, only based on such kind of restriction, that the d vector, displacement vector, can evolve. So that is the conclusion. So once again I'll write down ultimately the second conclusion. Okay, fine. So let me therefore quickly write down what is the second conclusion. Similarly, the one more curl equation determines the d vector, once again subject to the constraint. What constraint is that the divergence of d equal to rho all the time. So of course I didn't write all the time. Remember, divergence of d equal to all the time should be equal to rho. That is the meaning of dou by dou t. And of course that's all. So this is, so with that we are having the main conclusions. Of course, I already explained all these things, so therefore let me write down what are the important conclusions we made in today's class. So this is your second curl equation. So the second curl equation determines the electric field, subject to the constraint or restriction, whatever you call, subject to the restriction that the divergence of E equal to rho by epsilon naught. Of course, this is in 5 minutes back I was talking about displacement vector, right? That epsilon into E, that cross multiplication, what we are calling like displacement vector. Okay, so whether you write in that style or in this style, ultimately it's all the same. Okay, whether you want to write in terms of E or whether you want to write it in terms of D, electric displacement vector, that all depends on style of writing. If you want to absorb the epsilon naught inside, then it becomes d vector. That's all. So ultimately conclusion doesn't change. So these are very important conclusion, two important conclusion. And now we will count the number of equation. We were asking the number of equation was extra, right? So I will write down that conclusion. we have two scalar constraint equations. So this is our conclusion now. How many constraints are there? Two constraints are there. And what are the remaining equations? The remaining number of equation you have to count. So of course you should remember that there is one restriction here. This is one restriction, and this is the second restriction. That is why I have written 2. Remaining is 6. So remaining 6 equations are there that determines the temporal evolution. Determines what? That determines the unknown quantity. That's what you have to write down. So that determines the unknown quantities. So this gives you clear indication. Uh, we have been asking, no, there is some kind of a contradiction. Why we are having two extra equation? Now it is very clear. The two extra equations are doing the job of constraint or restriction. It is putting restriction on the electric and magnetic field. That is the job of the extra two equation. So if you remove the extra two equation, how many are left out? 8 minus 2 is 6. So those 6 equations are actually doing the determination of the unknown. Unknown means E and B field. So electric field time, there is a 3 here and there is a 3 here. So 3 plus 3, 6. That is the 6. So 6 scalar equations are actually doing the job of calculating the field itself, and the remaining two equations are taking, or it is taking care the so called bookkeeping job. Okay, accounting and bookkeeping. That's how you can understand. So ultimately, so we are able to understand in a much better way the Maxwell equation. And this is, and let me also write down one final important conclusion. All the four Maxwell equation are independent equation. This is very important conclusion. All the four Maxwell equations are independent equation, which means that none of them can be derived from the remaining. Or I will say that one cannot derive uh, one equation using the other equations. So this is also very important conclusion. Okay, we have already seen, of course, based on all our calculation only, we are making this kind of a conclusion. So with that, we are trying to we have reasonably understood in a much better way how the Maxwell equation itself is working, and then so that resolves the paradox, or that resolves the kind of contradiction that you have earlier. So now it is clear that only 6 scalar equations are there, and the extra two equations are only for the purpose of constraint. It is valid at all the time. That's important. Okay, so if you can go back to that board, we can see that. Yeah, so this is the place where we were saying that. So we now that the contradiction is, there is no more contradiction, and we have the unique solution to the set of Maxwell equation. There is no doubt about that, and there is no need to worry about more equation, less unknown. That kind of troubles are not there now. So this is the ultimate conclusion. So with this kind of understanding of the Maxwell equation, probably in the next class I would like to explain the gauge transformation and the gauges whenever you are having time dependent field. Okay, last class we have discussed the gauge transformation in the static field. The tomorrow's class, or the next class, we will discuss the gauge transformation for time varying electric and magnetic field. Okay.